In this video, we shall look at a few review problems associated with conservation of angular momentum. First, a brief introduction. Assume that a system is being acted upon by a net external torque. Its angular momentum would change with respect to time if there is such a net external torque acting upon the system. Mathematically, that net external torque equals the rate of change of the angular momentum of the system. That means if there is no net external torque acting on a particular system, its rate of change of angular momentum must be zero. That also means its angular momentum, namely the angular momentum of the system, has got to be a constant, or more accurately a constant vector. So if we were to compare the angular momentum of the system at two different times, characterized by initial and final state, we say the angular momentum of the system in its initial state is the same as the angular momentum of the system in a final state. And this statement here is known as conservation of angular momentum. Problem 1. Two disks are mounted on the same central axis so that they can be coupled and rotate as one unit. The red disk here has a moment of inertia of 4 kg/m², about that axis, and is set spinning counterclockwise at 500 radian/second. When we say counterclockwise, it's counterclockwise when it's viewed from top. The green disk has a moment of inertia of 6 kg/m², that's this one, about the same axis, with an angular speed of 800 radian/second spinning clockwise when viewed from the top. Find their common angular speed after they are coupled, like in this diagram. What is the direction of rotation after they are coupled together? So this is the initial state and that is the final state. So let's calculate the angular momentum of the system in its initial state. So there are two contributions, the angular momentum of that red disk and the angular momentum of that green disk in initial state. The angular momentum of that red disk is its moment of inertia, which is 4, times its angular speed, which is 500 radian/second in a counterclockwise direction. Now, if we take the counterclockwise direction to be positive, then the clockwise direction, as viewed from the top, has got to be negative. So 500 can be taken to be positive, 500 radian/second. Now let's compute angular momentum of that green disk. The moment of inertia is 6. The angular speed is 800 radian/second in a clockwise direction, so our sign convention says it's a negative number, so minus 800 radian/second. And that's going to give you minus 2,800 kg/m²/second. So that is the SI unit for angular momentum. Now let's calculate the angular momentum of the system in its final state, which is also pretty straightforward. Since now the two disks are coupled together, they will have a common angular speed. Let's call it omega. That is what we want to determine. They will also move in the same direction because they are now coupled together. Now, moment of inertia of the system is quite simply the moment of inertia of the red disk plus the moment of inertia of the green disk. So 6 plus 4, that is. So that is the moment of inertia. Now when we equate minus 2800 to that expression, you can determine omega, which is the unknown variable that we seek. So let's write it over here. Minus 2800 equals 10 times omega. So solving for omega, you get minus 280 radian per second. The fact that it is a minus sign suggests that the two disks will spin in a clockwise direction when viewed from the top, and that solves the problem. Problem 2. Figure below shows a rod with length 0.8 meters rotating about an axis shown. So this is the axis, and the axis is coming out of the board. Its moment of inertia about that axis is given by 0.15 kg squared. If the rod swings through its lowest position, so that is the lowest position, it collides with a mass 0.25 kg that sticks to the end of the rod. If the rod's angular speed just before the collision is 3 radian per second, find the angular speed of the rod mass system immediately after collision. So let's look at the initial state and let's look at the final state. The initial state is when the rod is about to hit the mass, but not quite. So in initial state, the mass is stationary. So let's calculate the initial angular momentum of the system. It is the momentum or the angular momentum of that rod plus the angular momentum of that mass, but we know the mass is not moving, so that is 0. The angular momentum of that rod is the moment of inertia of that rod, which we know it is 0.15 kg squared times the angular speed just before the collision, and we also know that it's 3 radian per second. Like that. So there we have it. The initial angular momentum of the system is 0.45 kg meters squared per second. Now let's look at the final state. How does the final state look like? So you still have that rod, but now the mass is attached to it, and they will move together as a rotation about an axis passing through the top end of the rod and perpendicular to the page. So let's calculate the angular momentum in the final state. The angular momentum in the final state is the angular momentum of the rod in the final state plus the angular momentum of the mass in the final state. The angular momentum of the rod in final state is its moment of inertia about that axis, and that number is given, times the angular speed after the collision, which is what we want to determine, omega. The angular momentum of that point mass is given by the mass, which is 0.25 kg times the square of the distance from the axis of rotation, and in this case it is just the length of the rod, 0.8 squared, times the angular speed of the system after the collision. Now we can equate this number to that expression and solve for the unknown omega. Equating the two, we get 0.45 equals 0.31 omega, and therefore omega is 1.45 radian per second. And that solves this problem. Problem 3. Figure below is the overhead view of a uniform rod with length 1.2 meters and mass 400 grams. It is rotating horizontally at an angular speed 25 radian per second about this axis right there. It is an axis through the center and perpendicular to the page, so the rotation is like that. A particle of mass 100 grams initially attached to one end of the rod is ejected from the rod and travels along a direction perpendicular to the rod as indicated by that blue arrow. Immediately after ejection, if the particle's speed u is 8 meters per second greater than the speed of the rod, and just after ejection, find u. So we need to know what the initial state is and what the final state is. An initial state is with the rod and that mass attached to the end, and the rotation is about this axis, and they're rotating together. The final state is when the mass detaches itself from the rod and start moving perpendicular direction like that, whereas the rod is spinning about that axis. Now the speed u, the speed of this particle, and we are told that u is 8 meter per second greater than the speed of the rod end just after ejection. So it is 8 plus the linear speed of that end. So let's assume that the rod is rotating with an angular speed of omega. So it is omega times this distance, which is half the length of the uniform rod, and that means it is 0.6. So if you know what omega is, you can figure out u. So let's calculate the angular momentum of the system in its initial state. So the first is the rod. The moment of inertia of the rod is 1/12 times its mass, which is 400 grams, so convert that into kg, times the length of the rod, which is 1.2, so 1.2, square that, times the initial angular speed of that system, which is 25 radian per second. Note that I have made use of the fact that the moment of inertia of a uniform rod about its axis that's going through the center is 1/12 mass squared of the length. Now to this we have to add the angular momentum of this point mass, and that is given by an expression like that. So this is the moment of inertia of that point mass, and that is the angular speed of that point mass. The moment of inertia of the point mass is its mass, which is 100 grams, meaning 0.1 kg. R is the distance from the axis, so half of the length, 0.6 squared. Omega is the same, 25 radian per second. Now let's calculate the angular momentum of the system in its final state. So again, first let's calculate the angular momentum of that rod. It's again given by its moment of inertia, which is 1/12, times the mass, 0.4 kg, times the square of the length, which is 1.2 squared, times the new omega, which we don't know, which is what we're trying to find so that we can find u. Now let's add the angular momentum of that point mass after ejection. So that would follow mr squared omega equation. So the mass is 100 grams, so 0.1 kg. The distance r from the axis is half of the length of that rod, which means 0.6 meters. Square that. Now what about its angular speed? It's not omega. It is actually u, the linear speed, over r, which is 0.6. I'm making use of the fact that omega is the tangential speed over radius. So this 0.6 will cancel one of the 0.6 from the top, and you can substitute u from that expression like that. Now using conservation of angular momentum, we can equate Li to Lf, namely this is equated to that above, and we can find omega. And if you do that, you can solve for omega as 19.3 radian per second, which after substituting into this equation will give you u as 19.6 meter per second. And that solves the problem. Thank you for watching.